Welcome back, folks. Let's do some physics. Let's look today at section 2.4. Acceleration is the title of this section. Now, I should say here at the get-go that acceleration is kind of a big deal. Okay? When we look at our first central topics for the fall semester, we're going to look at Newton's laws. That's coming up in chapter 5. Acceleration is going to play a central role in Newton's laws. It is fundamental. So it's important that we get a good grasp on it. Also, I'm saying this because acceleration can be tricky to get an intuition for. Okay, so I want to help you build that up over the next several lectures. We're going to define acceleration here. When I say lectures, I mean videos. Okay, so we're going to define it here, and then we're going to spend some time really over the rest of the chapter helping you get a sense of how the acceleration works. But before we get into acceleration, which is the main topic for our video here, I want to do a little bit of review of two big topics, the two big deals so far. Okay, well, there's position. Let's look at our picture here of the car. We've got a car moving along an axis, and as is conventional, it's not necessary, it's simply conventional, we have made the right the positive x direction. Okay, to the right is the positive x direction. We've got a car moving in that direction. Okay, the first idea, of course, that we talked about this semester is position. That is, remember, just the location along that axis. Somewhere there's an origin. I didn't draw the origin. You don't have to draw it every time. Okay, but position, in this case, you know, xi and xf. And you'll recall, because you're alert, that F stands for final, I stands for initial. So the car's initial position is here, and then over some time it moves to this position here. X sub I is its initial position, X sub F is its final position. Okay, and it required time delta t to make that move from xi to xf. And delta t is the final time minus the initial time. Oftentimes in problems, we set the initial time to be 0. We'll say more about that later. But if you're just watching your clock shows some time here at xi, and it shows some time here at xf. And to find out the total time it took to go from xi to xf, you subtract the two, tf minus ti, you get delta t. It's a positive number. Okay, so the car required time delta t to go from xi to xf. So the first big deal is position. Okay, the second big deal that we talked about is displacement, and this is all by way of review. And it is defined as delta x, which is defined xf minus xi. Xi and xf are simply locations on that axis, on that number line. Okay, but the displacement is how far the car went, how far it traveled. It's the final position minus the initial position. And remember, you will remember that displacement is a vector. Position is not. There's no direction associated with a mark on a ruler. It's just a mark on a ruler. It's just a hash on a number line, what do you call it? Hash mark, not a hashtag. I was going to say hashtag. It's a hash mark on a number line. There's no direction associated with it. It's just a mark on a line. So position is not a vector, but displacement is a vector. So let me do this over here. So position is a scalar. Displacement is a vector. I think that fits. Yes, that fits. Okay, the third big deal is the velocity. Okay, and the average velocity was defined as delta x over delta t, the displacement over the time. We could unpack this more. It's not really necessary, but we could unpack this more, break it down into our simplest possible terms here, like that. And because displacement is a, see, displacement delta x shows up right there in the definition of velocity, average velocity in this case. If delta x is a vector, then so is the velocity. So the velocity, like the displacement, is a vector. And this is a very intuitive understanding, right? In our example here, the car is moving in the positive direction, so it's got a positive velocity. In this example, the car's got a positive velocity. If it were going that way, it would have a negative velocity. Or alternatively, if we had defined left to be positive and the car were moving right, then the car would have a negative velocity. The velocity of the car is always determined by the direction that we choose to call positive. And the conventional choice is the right is positive. So that's velocity. All that now is by way of review. And we said more, right? We've said more, but those are the big deals. Those are the high points. Those are the clip and saves. Now, the next step, the next thing, the next big deal is today's big deal, which is acceleration. Did I spell that right? I believe I did. Yes, I did. How about that? Did you know that it's harder to spell things when you're up close to a board writing it? It's documented fact. I'm your science teacher. I'm not making this up. It's harder to spell things when you're up close because you get lost. You don't have a bird's eye view of the word. You get lost in the letter. So that's my excuse, ready and built in if I misspell things. Acceleration is also a vector. You'll be happy to know. And now the definition of acceleration is very similar to the definition of the average velocity. And this really is average acceleration. A is the symbol that we use for acceleration. The subscript AV tells you that it's the average acceleration. Okay. It is defined as 1, 2, 3 lines. You see how V average is defined delta x over delta t? A average is delta V over delta t. It is a change in velocity over time. In other words, there's no reason to assume, and we've said nothing about it, that the velocity of the car at point xi is the same as the velocity of the car at xf. Maybe it's speeding up. Maybe it's slowing down. Who can say? My point I'm trying to make here is that there's not only a location initially, but there's an initial velocity, and there is a final velocity. So it's xi and xi and vi, xf and vf. The car's velocity can change. When you have a changing velocity, you have an acceleration. Acceleration is a change in velocity over time, as you can see here. We can unpack this further. Vf minus Vi divided by Tf minus Ti. So that is the new big deal for this lecture, right there in the pink circle. The definition of acceleration as a change in velocity over time. If there is no change in velocity, there is no acceleration. If there is no change, delta V, that means there is acceleration equals 0. There's no change in velocity, acceleration is 0. And we're going to do plenty of examples of this. I'm just putting the idea out there for you. And to help you sort of get, I should say something about the units. The unit of acceleration, look at it, it's something about the units before I finish off the lecture here. It's delta V over delta t, so it's a velocity over a time. So the units of acceleration is meters per second, right? That's the velocity in the numerator. But then there's time in the denominator, meters per second, known also as meters per second squared. Those are our units, meters per second squared. And as we talk about acceleration, I'll unpack those units and help you get an intuitive sense of what meters per second squared means. Because every unit carries a meaning. That's one thing you'll learn here in Physics 102. All units are not just symbols that you stick on the end of a number. They have physical meaning. And we'll say more about the physical meaning of acceleration in just a moment. But first, I want to give you two simple cases here. Okay, what do we have time? 11 minutes or so. I think we're doing fine. Two cases. The first case, let me get my colors here that I need. Okay, so we've got our plus x-axis here. I'm going to redraw the car and just draw it in motion to the right. So its speed is to the right. It means velocity is to the right. Speed, remember, is a scalar. Speed has no direction. Its velocity is to the right. As I said, acceleration is a vector. If acceleration is in the same direction as the velocity, okay, V and A in same direction, okay, that means the car is speeding up. And this doesn't depend on what direction we call positive. Doesn't matter if we call the right positive or left positive. If V and A are in the same direction, the car is speeding up. So if the car is moving to the right and going faster and faster and faster, okay, that means that acceleration and velocity are in the same direction. Velocity and acceleration are different. Okay, that's important. Acceleration is not the same as velocity, but they can be in the same direction. In this case, they are. If they're in the same direction, the car speeds up. So when you're on the interstate, getting down off the entrance ramp, and you're speeding up and getting over a couple lanes, you're going faster and faster, your speedometer is going up like this, your acceleration and your velocity are in the same direction. Okay, that's the first case. The second case, you might know where we're going with this because you're all so alert. I can feel it through the camera. Again, positive X here. The car is still going to the right. You can have the acceleration be moving against the car's motion like that. When V and A are in different V and A in opposite directions, I think I have room for this. Yes, I do. If the velocity, right, this is V, this is A. If the velocity and the acceleration are in opposite directions, the car is slowing down. And not just true for a car, but for any other thing, a hockey puck sliding along the ice, what have you. Okay. When V and A are in opposite directions, the object is slowing down. When V and A are in the same direction, the object is speeding up. And that doesn't matter. It doesn't matter if the car is going in a positive or negative direction. Okay. whether if we moved positive x to be to the left, or if we had the car moving to the, if the velocity was to the left, doesn't make any difference. These are always true. V and A in same direction, speeding up. V and A in opposite directions, slowing down. You can take that to the bank because it is money. All right, so that's your introduction to acceleration. I'm going to do an example next. So you got that to look forward to. See you in video 24B. This is actually video 24. I dropped it here earlier. 24, I think, A. Okay, so we got an example, a worked example coming up.